2nd, we met last week.
We met last week. Did we study?
Yes.
Yes, we studied. That is great. So for the members who did not meet, unfortunately, I forgot to upload the recording. Assuming I remember, and I upload. But whether I upload it for this class or for that, you will access the one that you'll find there. So good afternoon once again. I remember sharing you with the notes. Those notes were for PowerPoint. Did you take a chance to go through and review those notes, or you were kind of very busy?
We did.
How about the rest? I'm only hearing 2 people. Others, what is happening?
We are on.
I'm waiting for others to also respond whether they went through or not.
We went through.
I did.
Okay, thank you for those who did go through, especially the links that were shared with you. Can I get a recap of what you got from there that was a side of what we discussed together here?
Okay. So that those were for the links of week 1. The two YouTube links.
Yes.
Let's see my notes where I wrote.
I want to hear a recap so that even members who were not able to go through, they are not left behind completely. Anyone who is willing to share, even if it's not complete, but somehow part of.
So last week, we looked at ideally 3 things. We looked at software. So we started with the program, and we defined the program as a piece of code to solve a single task. We went to the application, that's a combination of programs to solve a given set of tasks. And then we proceeded to software, which is a combination of applications that is ideally targeted to solve an end user business problem. And then under software, of course, we had different types of softwares: utility software, application software, and system software. Those are the types of softwares mentioned, but a few. We also talked about software versioning, like different versions of software. We looked at some history of software. You left us with some task of researching about open source and commercial software as well. Basically looking at the functionality and the mechanism. That's a recap of what we went through last week.
Okay. Now, as far as the links I shared are concerned, what did you pick from the links I shared with you? Not necessarily you who has been talking, but also other members who happen to access the notes. Can I have another person tell us? Okay, thank you. Can I have any other person? Do we have any lady on the call or you're all men? I would love to have a chance to give another gender. It is human to balance, isn't it? It is human. Can I have another gender share what they read about? If we have any. I think we don't have, do we? You had somebody to hide, and is Josephine available? Or-
Yes, I am. But I don't know, I'm in a noisy place a bit.
Eh,
Yeah.
We can manage.
you can hear something. She decided not to talk at all. Okay, anyway, that being put aside, we discussed a number of things. Yeah, I'm happy that members were able to grasp it, ideally, which is very important. And they have been able to do a follow-up. For starting today, I will be sharing another copy of the notes as I promised. That you will have the PowerPoint, which is also available on Planet, but I will also share some notes that are in a more elaborative manner to help better understanding of operating system as a course unit. So today we are supposed to progress on from where we ended last week as our next lesson. Today we are going to, we had our discussion last week, we zeroed it down to a main aim of the course, which I believe everybody is very much aware. And that course, that aim was that we are meant to understand how the operating system works. And as you may have heard from the first person and the next one, that there are several functions of an operating system. So we shall start with one of the major functions of the operating system, and that is what we call process management as a big issue. Process management as a big what? A big issue. Now let me share something. Let me share something, then we can start our discussion and we see how to progress on well. Progress on well. Just a minute. Just a minute. I remember also telling you to read about evolution of computers, of operating system, as in the generation and how they came into place. Okay. I hope you were able to go through that. Were you able to go through that? Okay, it is important that you do so. Very, very important. So, let us usher ourselves into process management. Process management, process management. Yet to share. Or those members who are on the call, are you at work or you are already home?
Madam, we are at work.
That's where I'm gonna make noise for everyone in your department.
It is fine.
One time I was busy greeting someone. This issue of online, they will cause us problems. I was busy telling somebody, give us the answer. I'm insisting, yet the person is someone who's boss and they are stayed in the same room, you know. When you, when you feel that you are the boss and your subordinate is listening, kindly you can post in the chat or you can excuse yourself. Sometimes we can't do without asking you to respond, okay? You can take it easy or you let me know, madam, please go slow. Okay, here we are. We are going to start with our main concept here, which is called process management. I believe and trust that you are seeing what I've shared with you. It has to do with the concept of process. Before we start on anything, unfortunately, I shared it before, before asking you. One of the things we talked about last week was a job, a task, a program. You will excuse my voice. I don't know what happened. I think I've been talking a lot. I've been in the meeting almost the whole day. So last week we talked about a task, a program, and then a software. And we saw how to describe a task. We saw a process, a job, and something. So before we can move ahead, we can reflect on the definition of a task that we had discussed previously, and we said it's something that has to be performed within a computer environment. So to be able to understand process management, we start from the basic, and that is knowing what is a process. However, we start by distinguishing a process from a job. So from your kind of perspective and understanding, can you help me understand? Can you help distinguish between a job and a process? Let me first stop sharing because people are going to be cheating. I don't want to raise cheaters. So what do you think is a job and what do you think is a task? Gentlemen and lady. Yes, please.
The difference between a job and a task or a job and a process?
A job and a process.
A job is something that a job is like a task, something that you can do, and you employ processes to do it. Then processes are within the job.
Processes are
Then
the job.
yeah, yes. Then a process is a step by step. Is evolved steps of doing something, a task.
Okay, thank you. I believe everyone has a way of explaining those. Who rose first? I think it was Sozi. Sozi. Mm. Mm. was a job and a process. Oh my God. Okay. Now, Tinker.
Yes, a job, in short, is the overall work or request, e.g., running the program. Then a process is the actual running instance of that program in memory that the operating system manages.
Great. I have another hand. Oh,
Yeah, that was me, but he has explained.
he has opened up your brain and answered you, gave
Yeah.
your answer.
Yeah.
Okay. I hear another person as I was going to share. Yes, Chiwewa.
Hello, good afternoon. A job, I think a job is an obligation, and a task is a delegation. Then a process is a series of steps undertaken to fulfill a task. That's what that's how I can define them.
Okay, thank you. And for those who never answered, what happened? For those who never answered, what happened?
We were learning. We can answer next time. We shall have another chance.
They will answer the upcoming ones.
Yes.
Okay. So and then we talk about a process. Most of you were having a good idea, and then someone whom you presented as your president, I think, nailed it. In simple terms, a job, now in the context of operating system, a job in simple terms, it is any task that has been recognized to be meant for processing within an operating system environment. While a process, it is a program under execution. Although when it comes to a process, it can be at different states, as we are going to see. It can have different attributes, as we are going to see. It can have different stages it goes through. It is supposed to have resources, as we are going to see. So yeah, basically that. But when it comes to a job and a process, we distinguish them in a way that a job is anything that has not yet been given the CPU for processing, and while a process, it is something that is already under the operating system execution. I was sharing one of the resources here where I wanted to, I'm still contemplating which resource should I share among the other, but I think let me share the other one, not this one. Let me try to size up, though this one has smaller font, which I can't format right now. Okay, so let me share and then we proceed from there with our discussion. Can you see what I've shared with you? Yes?
Yes.
Great. So in here, we are seeing, we are starting our next topic, which is number 2. The first one was about the overview of computer system and operating system. And then topic 2, it is supposed to be process management. It is quite a very detailed topic, but we shall have to eat it in bits. I call upon your attention and concentration, just like the way I said last week, that sometimes we can reach a level where things are quite challenging but it's not a hard constraint, only that whatever we talk about, we cannot see or feel or actually participate in telling or explaining how they function. That's why it can mean to be a little bit complicated. So I call upon you to fasten your belt so that we can move together. Where you feel you are a bit not together with my pace, you can let me know, and I try to soften, especially when it comes to concepts where we are heading. It is always important you learn the concepts before we can severally or repeatedly be using them over and over. So when you talk about process management, it has to do with how an operating system is capable of running. I would say capable of running, how it is capable of running, how it's capable of even starting, because the process, as we shall see, processes originate from different sources, both from the end user, it can be from hardware, software, or even other fellow programs. So anything in execution, it is called a process. So when it comes to process management, we note that every process that runs within an operating system environment or a computer system, it is executed or managed by what we call a CPU. When I was with the day students, I asked whether they have ever seen a CPU, or how do you describe a CPU? And they were able to tell me. I don't know whether you are capable of telling me, or you already know. I don't need to bother you. What do we go with? CPU. You are speaking on behalf of everyone.
We
Okay.
assume we know, and
We can assume that you know. Okay, so for anything that runs within an operating system environment, it must be executed by the CPU. So as we move ahead, I'll be talking about the CPU, I'll be talking about the processor. In a summary, the processor is part and parcel of the CPU, because it's the one that activates all the operations within a computer. So when I refer to a CPU, don't say this woman is confusing us. When I say processor, don't say the woman is really confused further. They will be used interchangeably. And we see that anything that can be running at a given time within an operating system, it is supposed to be referred to as a process. And this process should be able to go through a number of different stages. As someone said, that it is a series of different activities that are carried out to execute during execution to have a given task being achieved, which is very true. So we see that, we also note that that an operating system environment has got a number of different processes running at a given time, those that we have initiated as users and those that are initiated by other resources, as still we mentioned the last week. I would like to ask, for those who are on the call, whether they all know how to find out, how to tell which kind of processes are running on your computer at a given time. What is the procedure of finding out which processes are running on your gadget on the computer at a given time? Can I hear someone telling us how to access on Windows environment? Yeah. Sure. Thank you. Anyone who's using Linux? How do you access on Linux machine? Thank you. So if there was anyone who didn't know how to access, kindly, if you not grasped this, find some time to do a proper research and even practice it. So after knowing that when you access the task manager, now in reference to Windows operating system, which is our main, the most commonly used. Whenever you access that task manager, you are able to see which processes are running at a given time and their origin, which program has initiated those processes, whether it is from the end user application or the system files, to name but a few. And also, we need to acknowledge the fact that when a process has been created, has been initiated within an operating system environment, a process is supposed to have a number of different attributes. And those different attributes, we are going to see them from here down. But before we talk about the different attributes, let us see that the following, we can be able to describe the process management in a number of different ways. We can see processes being created, we can see processes being deleted, we can see processes being suspended or resumed, we can be processes being into synchronization or inter-process communication. So a process can exist in different forms and can contribute to different aspects that are happening within the operating system environment. When we talk about processes, and there are many running within an operating system environment, we can't fail to describe each process as it exists at a time. To be able to do that, we look at what we call process attributes. And we have a number of them that can be used to, can be associated with a given process. For example, each process is expected to have the process ID, it is expected to have the program counter, it is expected to have the burst time, it's supposed to have files that it will use, that is in terms of resources. It is supposed to have several, as we are going to see down here, for example, the state, the priority, then we have the list of opened files, to name but a few. Now let us see one by one. Those descriptions above can be used. Now when you talk about a process, each process has to be distinguished from the other by having, if you are you have already covered database, by having what we call a unique identifier, or what we would call a process ID. It uniquely identifies one process from the other so that there is no confusion when the operating system happens to call or involve a given file or a given execution amongst the many that may be running at a given time. So a process ID, it is mandatory, which cannot miss for every process. Then we see what we call the program counter. This is supposed to be there should be an address associated with a given process that can show the next process or instruction that is to be executed. For those who have already done computer architecture, you've already seen a number of different registers, and one of the most important registers is what we call the program counter. Then we see the process state. When a process is to be executed within an operating system environment, there are a number of stages it is supposed to go through. Right from the time when it is created, it is prepared for execution, it is forwarded for execution, it can be in a waiting or blocked state, it can be resumed, it can be completed. So those are the different stages or the different steps a process is supposed to go through within an operating system environment. We shall see the process model, the process state models as we move ahead, and we shall explain these different stages and how they work in connection with execution within an operating system environment. We have another attribute, which is priority. For every process, you know, since we have a number of processes which can be created at the same time or be recognized at the same time, there's need to have priority attached to each and every process so that we can get to know which one can be executed first and which one can be executed last. So priority can be given based on a number of different factors, or the approach of execution that an operating system is capable of what? Of implementing at a given time. The mechanism can be based on the type of operating system, and the mechanism of execution as well can be provided based on the source of the process, where it is originating from or where it has been created from. We have general purpose registers. These are supposed to hold information that is to be utilized by a given process. For any process to run within an operating system, the operating system is supposed to know exactly what should be involved. Just like the way you are admitted at, let us say, I will take an example of a primary school or a nursery school, where you are given requirements before joining. Besides paying tuition and besides being registered and getting an admission, there are some things you have to satisfy, you have to report with before you can attend your first lesson. Those are general purpose registers that hold information that will be needed at any given time at all different stages, properly prepared and made available when that process is to start execution. Then we have a list of opened files. You may have a number of resources or requirements you need to process, that is if you are a process, but at a given time T, during execution, a given process can require information from other files. So if those files are to be needed at a given time in the future during execution, those files have to be fully examined and refreshed and made available for this process before it can start execution. Why they are made available is because that they are trying to eliminate any possibility of that process being able to be delayed due to the inability to access those required files or required information within those files. Then the last attribute is the list of opened devices. We all know from our previous discussion that one of the major functions of an operating system is to manage the input-output devices. So if there is a process that has been created and has been originating from any of the devices, whether input or output or even internal devices, and at a given time that require exchange between the different devices, these devices that may be needed for either storage or retrieval of any of the files or referencing of any of the files must be made available and known and accessible before a given process can be run. You will take note that as you are trying to save, for example, if you had opened a file and it was on a flash disk, let us say, and then the flash disk somehow it was disconnected. If you try to save again, you would get a notification that such a device is no longer available. So it is the work of the operating system to make you aware that you do not start something that you can never end, or that can lead you into wastage of time, or even not be able to accomplish those kind of tasks. So to be able to prepare our process for execution, there is need to first attach attributes to each and every process so that it can be made available and can be recognized and lined up for execution when all these items are known. So that those are what we call process attributes. They just describe entirely what a process is all about, what it is, and what it may require when its time of execution comes up. Let us see the process states. I guess you are together. We are together. Are we?
Yes.
Thank you. So when we talk about a process, after knowing the different attributes of a process, we move towards what we call the process state model. Before we discuss this model here, I would love to put a proper statement that there has been a number of involvement of different process models because even the operating systems have been evolving over time. So we started with the two-state process model. I want you to research about the two-state process model. Then they advanced with the three-state process model. And now currently modern operating systems, they operate on the five-state process model, which is this one we are going to learn. So I want you to be well acquainted with the two-state process model and three-state process model. That explanation on how they function has been embedded within this main one, but the others also should be well known to you so that you can know that this never came from from anywhere, but it was able to originate. It has its origin. This is called a five-state process model because the entirety is supposed to have 5 stages. I want you to first use your eye to block suspended ready, and also use your eye to block suspended wait. The remaining states are the ones that mainly constitute the 5-state process model. Have you tried to block them? You block with your eyes. Well, assuming we have blocked with our eyes and you remain with only 5 states, and those will be new, ready, running, wait or block, and then termination. Those are the 5 states which constitute the 5-state process model. Now, we said that an operating system environment can have more than one process created or available within for execution. So when a process has been created, it is considered to be new. And when it is new, it means that there's nothing that is known about that given process. The attributes are not yet known, and the resources that will be required for execution are not yet known. At a creation state, there can be a number of different processes available at a given time or created at the given time. And if there are many, it means that at the new state, there must be what we call a queue. A queue as in a line. So at a new state process model level, there are very many, there can be many processes at a given it at the same time, and those many are supposed to be in a queue. When they are in a queue, it means that there is something to be done so that they can be recognized and be known and set ready for execution. What happens is at a new state process model, each process that arrives is the operating system struggles to attach a number of different attributes. The ones we've discussed above, and besides those different attributes, it is capable also of attaching time in terms of how much time a given process will require to execute up to completion. It also goes ahead to attach the memory aspect, how much memory that given process will require during execution and after execution for the results to be kept. We also need to acknowledge the fact that the moment the attributes are well known of a given process, memory has been established, the time for execution has been also estimated, then that means that that process is ready, can be dispatched, can be forwarded to the ready state for execution. When it comes to the ready state for execution, it also finds a queue there. Remember, the operating system works on all these things in microseconds. So it means within every 2, 3, 4, 5 microseconds, more than one jobs are created, and then after being created, they are forwarded to the ready queue. Maybe something I'd forgotten to mention is that at a new state process model, we do not necessarily say a process, rather we call it a job. Remember where we started from, and I said that a job, it is something that it is a task that has to be performed. And while a process, it is a task that is under execution, a problem that is under execution. So at a new state process model, we can use that terminology called job, or more so you can also say a process. But at a ready state, that's why we mostly acknowledge a process to be a concept we can use. So at a ready state, they also find a queue, which queue has a number of different processes available at that stage. What happens here in the ready state, it is that this is where the operating system is capable of now recognizing which job can run first before the other. It can be based on a number of different factors, but those factors are mainly related to the attributes associated to that given process. And those attributes are associated with that given process. They range from the time to be spent for a job to be executed. Also, another one which is very important is the priority attached to that given process. Allow me pick this call. Somebody is badly calling me up as you try to internalize up what I've been saying. Let me try to mute myself so that I can answer this. Okay, I'm back. So here we are. I was still explaining the ready state. So at the ready state, this is where the jobs are lined up. They go in a queue, and then the execution of each and every process is determined by its attributes. At the same time, the time that process is made to spend during execution. One thing I forgot to talk about is that at the new state level, we have a queue, and that is called the job queue. At the ready state, we have a queue which is called the process queue. So wherever we have a queue, there is also supposed to be what we call a scheduler. And when you talk about a scheduler, it is a mechanism that is implemented to be able to sort the different processes and make them ready to go through the execution process. So at the new state, where there is a job scheduler, that scheduler is the one responsible for attaching the different process attributes, and also the one responsible for forwarding that job to the ready queue to be ready for execution. So after attaching the attributes, it adds the time to be spent and also priority, as we discussed, and it also sources the different resources required for execution in terms of memory, and it becomes ready. When nothing is not missing, out of a given job that has been created, that's when it is sent to the ready queue. To the ready queue, there is no job that reaches, there is no process that reaches that level, which is when it is lacking anything. When it is forwarded to the ready queue, the process scheduler now comes into play to be able to analyze the available processes at a given time. They can be 2, they can be 5, they can be 10 or 20. It is capable of scanning through, be able to identify which one has the highest priority, which one has the less processing time, so that it can start with those as a way of maintaining efficiency in execution. Remember, one of the characteristics of a computer is the speedy and accurate delivery of tasks. So in order not to compromise the accuracy and not to compromise the fast delivery, the process scheduler, it is capable of scanning through in the interest of time and interest of priority, so that jobs can easily run through without any delays. When the job is set to be the next to be executed, remember it has a program counter. When it is set to be the next to be executed, it will be dispatched. That's why you see this arrow from above saying dispatch to running state. At the running state, under normal circumstances, each process is supposed to run without any disturbance up to completion. That is the completion state or the termination. However, we talked about under normal circumstances. There can be circumstances where there is need to take away the CPU or the processor from the currently running process, and it is that running process will be excused and it comes to the waiting state down here. That's why you see an arrow named the I/O to mean input-output request. An input-output request in computing, it is called an interrupt. An interrupt. An input-output request, it is called an interrupt. An interrupt comes from a highly prioritized process coming into the ready queue when there was already a running process. When there was already a running process, which has less priority as compared to a highly prioritized process, it will be requested to move away and surrender the CPU for a higher priority job so that it can execute and finish. In most circumstances, the currently running process under the running state will be taken to the waiting state. But if the higher priority job, or there are more than one job that has got higher priorities than the currently running process, then there will be no need of going to the waiting. They can actually take that process from running back to the ready queue so that it can take the next slot after the high priority jobs. I don't know whether that is understandable. Now, before we can progress, we've seen input-output request being called an interrupt. When an input-output request is granted, there are two things that happens. One is the operating system activates a given storage mechanism, which is called the process control block. The process control block. The process control block, it is a mechanism of storage that is used during execution of processes to store and keep all the information regarding the processes that have been submitted to the ready queue to be executed. Now, during the input-output request, when it has been granted, the process control block already has information about that running process. But since it has been interrupted, the process control block is supposed to add some more details towards that process which has been interrupted in terms of how much time has been spent during execution. It also adds how much memory has been utilized. It also adds which kind of files have been utilized. It also records the remaining time for that process to be executed and complete. That is why the process control block is called to be updated, so that when that job later is resumed for execution, it does not start afresh. It resumes from where it stopped. And it does not use resources again which have been used. Rather, it continues with those resources that have not yet been utilized. So one of the things that happen during the input-output request is updating of the process control block. Number two of the things that happen during the input-output request is what we call context switching. That concept called context switch or context switching, it is a process, it is a sub-process that involves accepting to release the CPU and allowing another process to be given the CPU and execute, and later that process that has allowed can be resumed. So context switching, it implements input-output request. Whenever there is a context switch, it means that there has been an interrupt that was allowed to be implemented. While when there was when a request comes in and it is not allowed to take over the CPU, context switching does not work. I request somebody to record because my recording has stopped and I'm trying to record again. It is refusing. So someone can help us and make the recording of this class. That is about input-output request. We have other two states that subsets of waiting, and then another one is a subset of suspended. Now, under very simple circumstances, when a process goes to the waiting state, it can exist there for as long as higher priority jobs are still running. If there was one or two higher priority jobs and they had very short execution time, it will give it a chance to quickly go back to the ready state for execution. However, there are circumstances where a job that has been interrupted to go to the waiting state can exist there for a short time, and another job also which was executing is also equally interrupted. So they become two, okay? And these two which are here at the waiting state, one of them has higher priority than the other. That means the one which has a less priority will be suspended further to suspended waiting. That's why you see there's an arrow coming from the waiting to suspended wait. When the job that remained in the waiting state has been called back to execute in the ready state, this job which was suspended will now come back to the waiting state, and also as it waits to be going back to the ready state. However, there are circumstances where more than two processes are interrupted. So the first one comes in the waiting state, another one also finds it there, a third one also comes in, a fourth one comes in. So that means the first one, which was first interrupted, has lower priority and it will be put into suspended waiting. Equally, as it is in suspended waiting, it can also get another one which will find it there, and vice versa. If it overstays in suspended waiting, then it cannot go back to waiting state. Instead, it can be now forwarded to suspended ready. Why does it go to suspended ready? It's because when a process overlays in suspended waiting, there is a probability that its time for execution can be consumed up. So when the time for execution expires from suspended waiting, it cannot go back to waiting. Instead, it will go to suspended ready. Suspended ready will now have to go back to the ready state, and it will be recognized as new. It will be recognized as what? As new. Equally, this suspended ready state can serve processes that have overstayed in the ready state without executing, because every time it is about to execute, a new job comes in with a higher priority and it does not get a chance to execute. So because of that matter, if a job was number one in the ready state, and then 5 more jobs come in, 8 more jobs come in, and they are all of higher priority, it means that it's going to be at the back of the queue. So what the operating system can do in order to eliminate the waiting time, it will put it in suspended ready, so that when it comes back, it will be recognized as a new job, which can be again scheduled for execution. When we talk about waiting time, when the job arrives at the ready queue, the process scheduler recognizes it and records its arrival time. When the arrival time has been recorded, it will be used to estimate how long the process has delayed in the ready queue before it was taken for execution. When a job overlays at the ready queue, it shows the inefficiency of the system. That means there is a delay in execution of a job. So one way of not accumulating the ineffectiveness is by creating the suspended ready, so that the process can be in a motion mode, not necessarily at the ready queue, but hoping to join the ready queue without having a lot of delay when it is waiting in the ready queue. So that's why suspended ready exists, and that's why suspended wait exists. There are reasons why a process can be switched, because remember I talked about context switching. There are reasons why a process can be switched from the running state to the waiting state. There are also reasons why a process can be switched from the waiting state to the suspended waiting. Equally, there are reasons why it can move from suspended wait to suspended ready. Also, there are reasons why you can move a process from ready to suspended ready and from suspended ready to the ready state. That's in summary what that diagram is all about. Whenever I'm discussing this, especially for people who are online, I always preempt you. I always ask you whether you can be able to explain that diagram. So I'm waiting for some answers from your side. Can you be able to explain that diagram from what I've been laboring to explain it to you?
To a certain extent, yes, but I have a question.
Please.
What determines the priority?
What determines the priority, it can be a number of things, but one of them is the source or the origin of a process. We have processes that originate from the system files. Those they have given a higher priority than user-related or application files or application requests. Given the fact that system files involve also operating system files, issues to do with their updating antivirus, doing what, or executing any timer or anything, they cannot wait. So anything else can be left aside and they are given a go-ahead. Another reason comes in terms of availability of resources. As we progress, we shall see that a process is supposed to procreate. When a process is executing, it can procreate one to multiple of children. And even the children of a process can also produce. When there are several of the sub-processes running, it means that you are utilizing a given one or two resources maximally. So if you are using given resources and they happen to run short, your priority might be reduced in favor of somebody who can utilize the resources available. However, not every procreation requires extra resources. Ideally, when a process executes and it procreates, it does not require any other resources. However, the maximum utilization, you can be given a location in memory, which I will also be learning about memory management, which you can be given a location in memory, for example, 100 MB. And that 100 MB was an estimated size of memory you can use. And during execution, a job might have been allocated that space, but it does not fully utilize it maximally. And then there is a job that is allocated, and when it fits there exactly, what we call the best fit. So when the job is best fitting a given resource, it utilizes it maximally. When it is underutilized, which is a bit of a disadvantage, but also it has an advantage at a given time, as we shall see. When it is underutilized, meaning there is some space which is not occupied at a given time, though it is allocated, it gives a chance to an incoming job, an incoming process to show appetite to run in the space that is currently not utilized. So if a job is of a higher priority, even if that resource has been given to that given process, which is underutilizing, it can cause that interrupt with the job with the higher priority to take away that job, to be given that resource, and it runs and it completes. I don't know whether I've been able to answer you, Adrian.
Yes.
Thank you. Any other question or someone who can be able to explain that diagram briefly? It is important you try than waiting for me to jump away from this slide, from this place here, because I may not be able to return. And also I take more time on this because there are many concepts that come into at the same time. that we need to actually internalize at this level. Anyone willing to try on how to explain this diagram?
Jalia.
Why her? Don't you know she's fasting? Even Fahad. Fahad, are you willing to
Also
try?
fasting.
Yes, I can try, and I'm fasting.
The brain is not fasting.
When I'm lying, I'm not fasting.
Okay.
Madam, first I don't know. Okay, I don't know why you're calling it a 5-state process diagram, and it looks like it's a 7-state.
Mm.
But then I will say at exactly where it's starting, where the new is, you just double click a program. The OS is setting it up, but hasn't put it into the main memory. That's in short, or hasn't put it into the RAM yet. Then the process is now in RAM. It's like standing in the line and then you have your money and ready, and the process needs the CPU to be free. So basically, in the run, the CPU is finally working on your task. The wait block, the process needs something else to happen before it can continue, like waiting for you to type something or a file to load. It's set out of the run line, so it doesn't waste the CPU's time. Termination, the task is finished. The OS cleans and deletes its record. Suspending, okay, this is sometimes the RAM gets too full. To fix the operating system, it swaps some process out of the first RAM and onto the slower hard drive. That's say the secondary memory. Then the same thing, it's also the process is ready. The suspend stroke ready. The process is ready to run, but it's sitting on the hard drive because there's no room in the RAM. And then suspend stroke wait. The process is waiting for an event, and it's been moved to the hard drive to save space. So schedule dispatch, the OS picks a ready process and tells it to run, basically. So the time quantum, the priority, if a process takes too long or maybe more important one shows up, the OS kicks it back to ready. So basically sends it back to ready. Then resume brings a suspended process back from the hard drive into the RAM. So that you can get back to the RAM. Basically, maybe in my own terms, I would say you can think of the OS as a manager of a busy kitchen. Ready processes and the ingredients prepared for the counter, which is the RAM. And then running is the chef. That's the CPU actually working one dish. That's it. It's just like that. In short.
Thank you. Any other person willing to try? You can see how people have tried to customize. Yes, to women.
Madam, for me, I have a question.
Please. Before you can ask, can I also try to clarify that in the beginning, I told you to make it, to use your eye and block the 2 states below, and it is called a 5-state process model. There is no 7-state process model. Depending on the references you go to, you can find those that are clean with the 5-state. However, for clarity, to be able to understand clearly the different circumstances that occur within a multi-programming environment, those aspects are also included in there, but they are not complete states per se. So, Tugume, you can carry on, please.
My question is, what's the expected time or the normal time for this process to complete?
There's no process yet, though. There's no process yet.
For this cycle?
It is a cycle that can either be fully utilized or underutilized. Why am I saying that? Is because under normal circumstances, we had 5 states. That is new, ready, running, completion, and then probably maybe waiting. So the most normal circumstances when you take the 4 steps: new, ready, running, and complete. Then the interrupt comes in because we are dealing with multi-programming environment. You find that nothing can move on smoothly. Just like the way your day starts, you expect you are waking up or do the preliminaries, go to work, run the normal schedule, and then return home. But along the way, before you reach home or before you sleep, you get something that has to call your attention, and you cannot run as expected. So that's how also multi-programming environments are working. So, but also we have to acknowledge the fact that an interrupt may not occur, may not only occur one at the same time. There can be multiple. That's why you see that we are able to have suspended wait, and later we can have suspended ready, meaning the abnormal circumstance can escalate, can go to a worst case scenario. Also, I want you to put in context of this. I always give an example in this way, though my colleague here said about the kitchen. You have all navigated the roads of Kampala here, and you see that during the peak time, we have a lot of vehicles from different angles of the roads and at different junctions. However, when you are using the main road, I would take an example in Entebbe Road because I stay that side. You realize that when there is a higher priority person, for example, the minister, the prime minister, the vice president, or at most the president, they will create a way for those people. And as they create way, you are getting interrupted. You will be told to stop for some minutes, and then you will resume. So that means that you had your plan to run a normal program, but later you were interrupted. You couldn't resume because you had a high priority person who came in, and you were able to what? To give way. You will forgive me. I also have an interrupt. I'm home. I stay near a mosque, and you can hear they are calling people for prayers. I hope you are not getting a lot of noise. So that's yes.
That is the perfect example. That is the perfect example. There's an interruption, basically.
Thank you. Okay, so do we have any other person, or it is clear to everyone? We can move ahead because I wouldn't love to move back and forth in case there's anything that is not clarified in that regard. Thank you. Thank you. So we can resume. Below here, as we move from our diagram, we are able to move to the next section, which explains what I've been talking about, what takes place on the ready state, the new state, the running, blocked, waiting, completion, and other things, suspended ready and suspended wait. They are all explained. I'll share with you these notes. I have a note here to research about the 3-stage process model. However, I also uttered that we research about the 2-stage process model. Now let us see, as we see, we have processes within an operating system environment. These processes can have a number of different operations to be performed. So what are some of the things that can be done on a process? Number one, creation. A process can be created, although also a process can create another process. Then also a process can be scheduled. After this lesson, we shall see process scheduling, which is the next thing. We talked about schedulers, we talked about the queues, and we shall see that for how does a scheduler, how is the scheduling done of a job, of a process. Another aspect is the execution. A process can be executed. A process can be deleted, can be killed. That word is maintained by virtue of the concepts within an operating system. They don't say, do they murder, do they what? The way you understand the word kill is that killing. And also, we see that we have a number of different schedulers, which I told you about. We have the job scheduler at the same time called as the long-term scheduler. Then you have short-term scheduler, the same as the process what? Scheduler or CPU scheduler. And then we have mid-term scheduler, which operates between the inter-process communication, that is between the input-output interrupt. During the interruption, another scheduler happens to exist, which is called the mid-term scheduler. It supports the context switching to take place within an operating system environment. I talked about the queues, and the first one is the process queue. We also have the job queue, and then we have the waiting queue. One thing I need to put across is that everywhere where there is a scheduler, where there is a queue, there must be a scheduler. Whenever there is a queue, there should be a scheduler to be able to put order into that place. And every time we have a queue, we have a scheduler to work at that place. So whenever you hear long-term scheduler, mid-term scheduler, there is also a queue that is associated with that. Now we have this diagram here that shows the transitions of queues. It tries to show how the execution happens, somehow replicated from the other 5-state process model, which is not much of effort needed here. We have the job queue, which I already told you, it happens at a new state. We have the ready queue, it has the process or short-term scheduler, and then we see the CPU, then the completion. Whenever there is an input-output request, which is below the CPU, we can go to waiting, and also an event can be allowed to execute based on a given priority. It can be time, it can be any kind of source. And then all these requests that come in, the interruption and the context switch that happens, it should be able to lead this process to going back for execution under the normal circumstances. So we do not, amidst all these interrupts and context switching, there is no possibility of expecting a job to fail to run within a CPU environment or within an operating system environment. However, as we progress, we shall find a terminology called deadlock. We shall describe it when we reach it, but at this level, we assume that everything will run perfectly well, irrespective of the interrupts, irrespective of the context switch that can happen on a given job within an operating system environment. So this explains the queues that I was talking about, the waiting queue and others. Now, allow me, at this time, I always like to end on this diagram here. I don't know whether you can see it properly. I wanted it to size it, but the format in which I put the work also is not helping. Let me just do like this. Can you see properly? All right. Now there we are. As we were explaining the process state model, I kept on mentioning some key concepts relating to time. And we talked about arrival time, talked about waiting time. We talked about burst time, completion time. We shall see turnaround time, average turnaround time, to name but a few. So I always don't like explaining this diagram here, but I always put it there so that you can encrypt it into your mind. Try to first think out loud. What does this mean? Rather than me giving you the definition is below. Arrival time is this and this. Waiting time is this and this. Burst time is this and this. Then completion time, this and that. So I want you to check through everyone who's on the call. Try to tell me, how do you explain arrival time? based on this diagram, because these arrows clearly depict what that concept means. So without much ado, I want to hear people telling me, choose any time you want there. We have a lot of time. We have a lot: arrival time, waiting time, burst time, completion time. We have turnaround time. Turnaround time is TAT, okay? Then there's also what we call burst time. We have also, which other one? That is all, I think. So who can explain to me those different times? What does it mean when somebody tells you waiting time? I hope I'm still on the call. Am I?
Yes. Yes.
I'm on the call, so they stop telling lies.
So the arrival time is that basically when the programmers are, did I say program? When the job arrives at the ready state, that's the arrival time. And then from the arrival time until when the program can actually run, that's the waiting time. Then from the waiting time, the time taken for the program to run, right from the run state to the completion, is the burst time. Then there's time taken. Okay, Paul.
Why? You continue.
Then from if the total time taken from the arrival time all the way to the completion time is given, what's that name? That should be the run time or something like that.
I'm listening. Are you done, Edwin?
Yes, I'm done.
Okay. Any other person willing to try something? Mhm. Okay, that is good. Everyone has something he has added across. Can we hear from Fahad?
Madam, I think he explained everything, right? The arrival time is the exact time the process enters the ready state. The waiting time is the total time a process spends in the ready or like in the queue before it finally gets to run. That is the waiting time. The burst time is the actual amount of the time the CPU takes to execute the process. The completion time is when the process finishes its execution and exits. The turnaround time is the completion time minus the arrival time. It's the total time the process spent in the system. That is the waiting time that was there, and then plus the running time. That is the whole total. The turnaround time. The waiting time is the turnaround time minus the burst time. It tells you exactly how much time was wasted just sitting.
Okay, thank you. There are also other concepts that come into play which have not been represented in the diagram. For example, response time and also CPU utilization. There is also what we call throughput. There is also what we call quantum. Yeah, a lot. So who can guess what is response time? depending on the diagram, because you say the turnaround time, it is completion time, time is arrival time, then the waiting time, it is turnaround time minus bus time, etc. So as you internalize that diagram there, what do you think is the response time? Yes, please.
Madam, I think the response time is the time taken for the computer to respond.
Okay. Is it a computer? We have to substitute the word computer with the process. Relate every time.
Yes. The time taken to complete the given task, or complete the processing, the job processing.
Literally, it can be that, but there is also another way of explaining it. I saw somebody else's hand up. Who was that? Was it Sozi? Fahad.
The response time, I will take it as the latency when it comes to like internet, like that. It's basically the measure of how snappy or reactive the system feels to a user.
But I want you to use the word process.
So it's a process. It's a process. Well,
Yes.
response. I can only use the word time.
Only use the word time. Well, that is it. Noted. We have definitions in here below, of which I will not want to read through. I don't like reading. I have to put a disclaimer. Very well. I don't like what? Reading when I'm in class. It bores me. But they are all put here. What is waiting time, response time, among others. I hope you can see, but I'm going to share this. You're going to read through here. Even you'll find, as you progress, you'll also find something called the quantum and other things as we approach scheduling. So let us just give a smaller something about CPU scheduling, which we shall be handling at length in our next lesson. About CPU scheduling. CPU scheduling, before that definition itself, it is a concept that was brought in to overcome the weaknesses of single programming operating systems that existed from the earlier operating systems as a way of avoiding conflicts and avoiding making mistakes during execution. There was need to establish a number of mechanisms to allow scheduling of very many jobs or processes that occur within an operating system at a given time. And within multi-programming environments that we saw in our previous lesson, the different types, you can clearly see that there was need to have a mechanism to streamline on how processes can be scheduled, how can be processed amidst them happening at the same time. Along with this CPU scheduling, there were a number of different provisions that were provided. For example, and we were talking about of context switching, to be able to allow to give a time slice of another job that may be of good importance or higher importance to be processed among others. There is also an explanation here of a process control block coming in among others. Then what happens when the context switching is being carried out, or how does the process control block handle the resource details. All these come in as a way of explaining the scheduling mechanisms, how they were wired. Excuse me, I have an emergency as well. Let me pause. Okay, I'm back. As I was explaining earlier, that the process control block helps to take track of each and every process that has been created within an operating system environment, but it is more updated. It is always updated whenever there is context switching. So we talked about, and still more information is provided in here. However, whenever there is context switching, there is another attribute that is added, which is called accounting information. Accounting information section is the one that gives the details of how much, in terms of time, in terms of resources, has been utilized and how much is required for a given process to resume its execution. Then we see reasons why we carry out scheduling. There are a number of different reasons why we carry out scheduling. One of them is to maximize CPU utilization. Have you ever come across where somebody is given liberty to do anything at their given time and it will never end? So in order to make a good use of the CPU, there's need to have scheduling being done. Then to have fair allocation. Look at how I typed the word fair. Fair allocation of what? Of resources or the CPU itself. You know, even in real life, if you've been gathered like 10 people and they make you enter into a room full of cash, all right, scattered cash, it would mean that people who have a lot of energy are the ones that will get a lot of money. But in order to have fair allocation and fairness for all processes, whether small or big, whether you have higher priority or not, there's need to do allocation so that everyone can have a chance to utilize the main resource, which is CPU. Then to maximize throughput, you know, sometimes when you do not become accountable, what has come in, what will go in at this time and what will come out, you may not be able to notice how much you have done, how much you've achieved at a given time. And of course, other reasons that have been given here. So next week, we shall be ushering in the different scheduling algorithms, different process scheduling algorithms. And they come in the form of first come, first serve, round robin, shortest time first, shortest remaining time. Then you have round robin, we have priority scheduling. You can even feel free to go ahead, because all these that I'm explaining here, they are in the links. We have videos that explain these things within the PowerPoint file, which I shared with you. So feel free to read and go and visit those links so that you can come when you're well acquainted. And the next time when we come onto here, we shall be doing some hands-on work, because during scheduling, there's some calculation that is taking place. So ensure that as you come to class, you have a pen, you have a paper, or you know how to use your application very well so that you can illustrate at the end of the day. As I tell you, share your work, you are able to share your work on that. And those who may not be able to be seated on the computer, I always tell you to come with a pen and a paper so that when you're done, you can snap, share in WhatsApp, and somebody else can what? Can project for us. Are we together?
Yes.
Yeah, so next week we shall start with these scheduling algorithms. Please, you read through, I'll share these notes prior. Even you have the links. So whatever was not covered in that main PowerPoint file, I put in the links to overcome those weaknesses. So we shall see the different examples, how to calculate, how to find those, and also practice more those time, so that we can be well sorted by the time we come to class next week. So I call upon any questions if there are. If there are no questions, I can call it weekend for me, and I let you go. Yes, Andrew.
Madam, can you repeat? I didn't understand what you were saying, that someone can show on WhatsApp. Is there any assignment for us to do?
No, I said during class next week, next Friday, you come with a piece of paper or papers and a pen, so that if you're not seated on the computer, you shall have some assignments to be done in class during the process scheduling. You apply how to apply the different scheduling algorithms. So make sure you are well acquainted and you can be able to write down. After writing down, you take picture on your paper and then you post in the WhatsApp group. Then you can project here to see the answers you've come up with.
All right, thank you.
Okay. Any other person having a question? Today, I've not heard from Melinda. I don't know whether he's okay. Melinda, you don't look to be fasting. What happened?
Madam, I talked.
You talked a bit.
I explained. I'm Chiwewa.
Chiwewa.
Yes.
Are you Chiwewa? Yes, Chiwewa. That is Melinda. How about Biabasaija? Are you on the call or you left your grandchildren on the call?
Much available, madam. I'm here.
Jalia, today you never said anything. What went wrong? Is she on the call?
She is.
Plus another person there whom we had chosen in the beginning, she dropped. I'm not seeing her. Then I think that is us. Twesije, I think is Twesije, isn't it? Twesije, have you ever said anything in this class, my dear? Well, all right. Let me wish you a nice weekend. I would like to appreciate the person who recorded last week and shared, so kindly do the same.